There's a growing consensus in the AI research community right now that while the capabilities continuously progress, these models are missing something fundamental. That is, these models cannot learn continuously on the job. The neural connection in its brain, the model weights, they are fixed. Every time you start a new conversation with Claude or ChatGPT, it knows nothing about your project, your code base, your preferences. It's like working with a brilliant colleague who has total amnesia every morning. This is the continuous learning problem, and it's led some of the most smartest people in AI to push the AGI timelines further out. Dwarkesh Patel, whose podcast is basically required listening if you follow AI seriously, recently updated his own timelines partly because of this. But here's what I think the discourse is missing. What if continuous learning isn't actually necessary for AGI? In this video, I'm going to walk through two concrete pathways to AGI. They don't require solving continuous learning at all. And I am not speculating, parts of this are already working today. First, let's set the stage. What's the current default plan for reaching AGI? Most frontier AI labs are converging to the same basic strategy. Step 1. Build an autonomous AI researcher, a system that can do the work of an AI scientist. Step 2. Recursive self-improvement. The AI makes a smarter AI, which in turn makes an even smarter AI, and so on. This compounding intelligence explosion starts solving problem after problem, not just software, potentially robotics, material science, drug discovery. Dario Amodei calls this the genius in a data center scenario. It's a compelling vision, but it has a dependency most people gloss over. The AI researcher needs to learn continuously. It needs to read papers, run experiments, build on previous results, accumulate understanding over weeks and months, and current models can't do that. The context window is a hard ceiling. Claude's current context window is a max of 1 million tokens, which is maybe 750,000 words. That sounds like a lot until you realize that a single large code base can be tens of millions of tokens. But it might be the case that we don't need continuous learning. Here is the core idea. Think about how a human tackles a massive project. You break it into pieces, you learn about what you need to learn, you hold the big picture in your head while working on the details. This requires continuous learning. You're constantly updating your mental model. An AI agent can't do the second step, the learning part. Every time it starts a new task, it starts fresh. But what if it didn't need to learn because it could coordinate with dozens of copies of itself instead? This isn't theoretical. Let me give you a concrete example. I recently used Claude Code's Agent Teams feature to write an entire book, a comprehensive textbook on LLMs. I spawned 25 agents simultaneously. Each one worked on a different chapter. They coordinated through shared files, divided the work, and produced a coherent 25-chapter book. Now you might say writing a book is an easy case. The chapters are mostly independent. Fair point. But here is where it gets interesting. What if you trained agents through reinforcement learning to be specifically good at coordination, not just at coding or reasoning, but at the meta skill of dividing work, communicating state, and synthesizing results from parallel workers? You would set up RL environments where agents are given complex tasks like software engineering projects, research problems, and they're awarded for not just getting the right answer, but also for how well they coordinate. They learn to divide tasks, create sub-agents, share context efficiently, and combine results. The ones that coordinate best get the highest rewards. This can completely fit within the current paradigm of verifiable rewards required by the second phase of LLM training. And this might already be happening. The Agent Teams feature that I just mentioned might have been built using reinforcement learning like this. Now here is the key insight. You might think, but without continuous learning, no single agent has the big picture. And that's true. But think about what having the big picture actually means for a human brain. At any given moment, even a human expert who knows everything about a project is only accessing a tiny fraction of their knowledge. They're pulling relevant pieces into working memory, reasoning about them, then putting them back. The full picture is never actually in their conscious mind all at once. An AI agent system can replicate this with external memory. When a swarm of agents starts working on the problem, the first thing they do is explore, understand, and write structured summaries. They create a knowledge base, organized, indexed, accessible. Then the main coordinating agent knows exactly where to look for that information. It's not continuous learning in the traditional sense. The weights, that is, the neural connections of the artificial brain, don't change. But the system as a whole accumulates knowledge, organizes it, and acts on it. And if the agents are superhuman at this coordination, because they have been specifically trained for it through millions of RL episodes, the result could be indistinguishable from a system that can actually learn on the job. The second path is more straightforward. What if the context window just gets big enough that continuous learning becomes irrelevant? Let's look at where we are. As of early 2026, Claude's context window is at 1 million tokens. That's roughly 750,000 words, about 10 novels. 2 years ago, the best models had 8,000 tokens. That's a 125x increase in 2 years. Now, Dario Amodei has publicly said that scaling the context window is mostly an engineering problem, not a fundamental research barrier, an engineering problem. Let's think about what 100 million tokens actually means. That's roughly 75 million words. For reference, a person reading 8 hours a day every day can read about 15 to 20 million words per year. So 100 million tokens is approximately 5 years of full-time reading. Now think about what that means for the continuous learning argument. If a model can hold 5 years of study material in its context window, and it can process and reason over that material instantly, is that functionally different from having learnt it? There's a concept in machine learning called in-context learning. The model's ability to pick up patterns and adapt its behavior based on what is in its context without any weight updates. And models are remarkably good at this. They can learn new tasks, adopt new formats, even pick up entirely new concepts just from examples in the prompt. So if you combine a 100 million context window with strong in-context learning, you get something that looks a lot like continuous learning. The model reads everything it needs, reasons over it, and produces expert-level output. The weights never changed, but the behavior is indistinguishable from a system that learned. And yes, there are technical challenges. The quadratic cost of attention makes long context expensive. But these are just engineering problems that are actively being solved. Now here is where it gets really interesting. These two parts aren't mutually exclusive, they compound. Imagine a system where you have agents with 10 million context windows, each one holding vast amounts of relevant information, and they're superhuman at coordinating with each other. One agent holds the full context of the code base, another holds all the relevant research papers, a third holds the project history and design decisions, and they have been trained through RL to work together seamlessly. That's not a system with continuous learning, no weights are being updated, but it's a system that can tackle problems of arbitrary complexity, accumulate and organize knowledge, coordinate across specializations, and improve its approach in real time. That starts to look a lot like the genius in a data center that Dario Amodei described. So when people push AGI timelines further out because of the continuous learning problem, I think they're making an implicit assumption that the only path to AGI runs through continuous learning, but there might be more viable paths. Now I want to be clear about what I'm not saying. I'm not saying continuous learning doesn't matter. It absolutely does. And solving it, in my opinion, would mean we get AGI. We'll talk more about that in future videos. Let me know in the comments, do you think continuous learning is necessary or can we get there without it?